Okay, sorry about that, guys. We had some technical difficulties. So in this video, I'm just going to show you the demos that we showed in class, okay? So for synthesis, whenever we're creating something new, I have this particular reaction. I'm going to add the classic vinegar and baking soda together. So you can do this reaction at home. I'm going to scoop my computer away so that you can see certain things. So here we have some some baking soda that's already in here. I'm going to pour in some vinegar. None of this smells good, by the way. And I get this kind of bubbling up that looks kind of like carbonation if we think about like opening up a can of soda. So what's happening is the baking soda and the vinegar are reacting and they're forming three products. They're forming sodium acetate, they're forming water. So we see like water still left in here. And then also carbon dioxide gas. So as that carbon dioxide gas and that water separated from each other, the carbon dioxide gas escapes and the water is still trapped in the cup. So this now has sodium acetate, water. It's still a little fizzy, a little bubbly, where that carbon and that hydrogen are separating. Okay, so that's the first one. The second one we just talked about. So that's our example for synthesis. Our example for the decomposition reaction is if you have seen hydrogen peroxide, H2O2. And hydrogen peroxide is usually kept in a brown colored container. And the reason for that is because hydrogen peroxide, if left open or left in a clear container in which it's in the light, will actually react and it will form two things. It will deassociate, it will decompose, and it will form hydrogen gas and oxygen gas, neither of which are very helpful if you're trying to either clean like a cut or use for the many things that we use hydrogen peroxide for. Hydrogen gas and oxygen gas are not really going to help you out. So that was our example for decomposition. Now for combustion, my ability to light the table on fire was largely unsuccessful, and I think it has something to do with the types of table surfaces we have in class, which is probably for the best. But if I just light this candle, okay, so here I have a candle that is lit. This is not product placement. Since this candle is lit, let's talk about what combustion is, because combustion is a really specific thing, right? It's a very specific reaction. Combustion is the idea that this candle, what's burning right now? Well, the thing that is burning is wax. And what is wax made out of? Well, most waxes, both candles and other waxy substances such as soap, are made out of animal fat. So they're made out of fat from animal, like discarded fat, like from cooking or from other different things from different lye. We can now manufacture like fake animal fat, but it's got like the same compounds. It just didn't come from an animal. And we can put those things, we can liquefy them and then pour them till they turn solid, and we can pour them in different shapes, in different molds like candles and soap molds. But it doesn't change the fact that they're all basically carbons and hydrogens. So the thing I want to talk about here is that this wax burning is carbon and hydrogen. I am currently in a room filled with oxygen gas, and by providing a little bit of extra energy in the form of a spark, a little extra heat, making these react closer together, I am now burning down the wick, which is making the candle wax hot enough to also burn, and some of it is escaping into the air as water vapor, as carbon dioxide gas, and also in the form of like a little bit of ash, a little bit of soot probably. If I blow this out, really got me there. Then the smoke that forms, we see some of that water vapor going away. Okay, so those are all the sort of basic ones, the kinds that you maybe could see every day. By the way, I'd like to point out this baking soda and vinegar is still going. It's crazy. All right, I'm going to pause it for just a second in order to put on my safety gear. Okay, so in this reaction, we're going to form a single replacement that I'm really hoping works because it's super cool, but I'm a little worried I might not have enough acid left. So we're going to give it a shot. So I have the equation behind me. We're going to have zinc there we go, plus hydrogen HCl, which is hydrochloric acid, is going to form zinc chloride and hydrogen gas. So we're going to see that in a couple different ways. First is I'm going to get away from that. I'm going to take some zinc pellets, so you guys might be able to see this okay, maybe, yeah. All right, I'm going to put some scoops of zinc down in here. They're just like little silvery, try to put it close to the camera to see, kind of silvery things. Okay, guys, so, I put the hydrochloric acid in the beaker. Zinc is in the balloon, and we're going to dump it in and hope that it forms. And it's not doing it. Okay, dang it. Oh, you're fine. I wanted to see if I could show you too. Okay, so this is what happens when our acid is too diluted. Basically, I'll try to see if I can get a better example of this later, but this balloon is filling up with a little bit of gas, but not a whole lot, because most of this hydrochloric acid has been used up already. And so the zinc is just forming in a pile at the bottom. What we should have seen is that as it made hydrogen gas, it should have bubbled, blew up this balloon, pretty big. The other ones in classes were like about this tall. So not the full size, but pretty big. And I would have felt the glass get really hot. So unfortunately we didn't see that. Sorry, we'll try again. You can still see some hydrogen gas. This is not for me, okay? So let's do our next one. So here we have some water. I'm going to put in a couple of sodium hydroxide pellets, NaOH. 1, 2, here. And, okay. So we are going to stir these up just a little bit in the water. So right now I have NaOH, and I'm going to also get a dropper. Okay, now we have all the stuff, all the things. Super fun. Okay, so we're going to put a couple drops in this. Doesn't take a whole lot. Okay, and you should see, this one's pretty cool. I like this one a lot. So sodium hydroxide mixed with water. I added a few things to let you see the color that is happening right here. So it is very pink, very purple. And now I'm going to add some hydrochloric acid, which again, I'm going to have to use quite a bit of, it seems, unfortunately. And we are going to keep mixing this until we get another color change. Nope, not quite yet. Okay, getting a little bit better. Ah, there we go. Oh, it's coming back. Okay, so that completely reacted with the sodium hydroxide, the hydrochloric acid did, and it formed this equation behind me. So we have sodium hydroxide, NaOH, plus HCl, forms water and sodium chloride. And what is sodium chloride? It's table salt. So this particular beaker, which by the way, sodium hydroxide is not great. It's very toxic. You don't want to get your hands on it. It is a little explosive. And hydrochloric acids are really strong acids. So none of these things are safe, right? And yet they combine together, this double replacement reaction, and they make something that's just water and salt. So this kind of gives us an idea about two different things in chemistry, which is number one, dose really makes the poison, okay? So everything is bad in large amounts, and everything is also probably safe in really small amounts. It's just deciding what is small and what is too big for certain things. Too much water means you're probably drowning, and too little water is also not great, but there's always a right amount. And the other thing is the idea that chemicals prefer to return to certain states than others. Certain things are energetically, it's a hard word to say, more favorable than others. Okay, so those were just some demos and some cool things that we did as a sort of example, and a really cool example of all of those things. Thank you.